Hello, everyone. Hello, my name is Adam. I work at NVIDIA. I'm a deep learning solution architect. What it means is, basically, I help companies build AI products. NVIDIA, as you know, sells GPUs, so processors, and I help people use our hardware better and help them translate their ideas into real products. And today I want to talk to you about two things, and two things only. So I want to give you a brief overview of how we are perceiving the last 5 years, how NVIDIA is perceiving the progress, especially in deep artificial neural networks in the last 5 years, and equip you with a set of utilities to very quickly assess which projects are and which projects are not suitable for this technology. So I'll leave you with 5 heuristics that you can use to do initial feasibility assessment, if you wish. And so, as you might know, I'll start with a bit of an introduction that I stolen from Andrew Ng. As now, neural networks are not a new algorithm. They've been around for at least a couple of decades, if not more. And they are actually surprisingly simple. So what you're seeing here on your left is just a single neuron. And all of you that do classical machine learning will immediately recognize those equations. There is nothing that special about it. A neural network is just an agglomeration of those neurons, and in modern neural networks, we put really a lot of neurons to make those algorithms work. So modern networks will have anywhere between 50, 60 million parameters when talking about image processing, to 100, 200 billion parameters when talking about natural language processing and speech recognition. So why haven't we historically used them? Why a lot of you haven't heard about practical applications of neural networks before? And the reason is simple. They just didn't historically work. So 5, 7 years ago, they were perceived as a failed experiment in machine learning. And the reason for that was very simple. So when you look at classical machine learning algorithm performance, you'll usually see that with the same set of features, the performance of that algorithm grows at a certain rate as you increase the dataset size. So the way you would usually increase the performance of your classical machine learning algorithms was to look at the data, its quality, look at features, do some smart feature engineering. And this is a way of moving this curve up and down. So to be able to improve the performance of your classical models. And historically, neural networks performed actually really badly. We didn't know how to build large models. They were difficult to train, and their overall performance was really quite unacceptable. And especially the progress that we've made with support vector machine led to them dying for at least a decade, which people are referring to as AI winter. But what happened recently is actually quite simple and led to resurrection of neural networks. That is, suddenly, for the first time in human history, we have huge amounts of data, and the community that you're seeing today is one of the reasons why we have such a huge amount of data available, and we have compute power required to process that data. So what we found in about 2012 is that those neural networks that were really struggling to perform on small data sets, and that's the state-of-the-art data set in 1999, and with small number of parameters, they really started excelling as you just simply increase the amount of data. And the breakthrough came really in about 2012, when a submission to an ImageNet competition, so a competition where the goal is to classify images, so distinguish cats from dogs from tables. The submission in that year managed to beat 20 years of vision research by about 20% in terms of accuracy. And that was simply because of this relationship between the amount of data and algorithm performance. So what we have been seeing since then is that neural networks continued to grow, and the data sets available continued to grow as well. And as a consequence, that discrepancy became higher and higher. More interestingly, what neural networks offer, and this is very clearly shown in this picture, is the fact that not only they behave better with the increased amount of data, but it's actually fairly straightforward to improve their performance up to a certain point. you can simply provide them with more data and build larger models, and in general, they behave better. And they are, and that's not just an empty statement of mine, that's not just something that we're saying, but that's actually empirically proven. So I'm showing you two very good papers that illustrate linear relationship between the amount of data and performance of algorithms. Academic references are here, and I was told that this presentation will be distributed to you as well after the talk. And as a consequence, they just miraculously, to some extent, started working. Okay, we figured out how to build bigger models because there were certain algorithmic challenges in building such large models. But since they started to work in about 2012, we have been seeing a huge trend towards larger and larger neural networks, as seen in this slide. So modern speech models are extraordinary. So 8.7 billion trainable parameters. To put 100 exaflops into perspective, it would take you a good couple of years to train that on a single CPU socket, just once. And in some use cases, like in automotive, training the neural network once on a single GPU this time would take you decades. So this shows you more or less the order of magnitudes of models that we're talking about. And that generated a lot of excitement and created the new possibility. So what I'm going to show you now is, for you it might be just a marketing video, but that's a set of projects that me and my wider team, so solution architects, that we've been working on throughout the last year. So just have a look, and that will hopefully help you to understand why we're seeing the level of excitement that we're seeing. And we need audio for that as well. We really do need audio for that. Thank you.
I am a visionary, exploring a universe of data to sharpen our view of the most distant galaxies. And studying black holes to help prove Einstein's theory of gravitational waves. I am a healer, giving doctors the power to turn mountains of data into life-saving breakthroughs. Identifying diseases like leukemia from a simple drop of blood, even in our own homes. And finding new ways to bring cures to market faster. I am a protector, keeping our oceans safe from invasive species, and helping our crops flourish while minimizing pesticides. I am a helper, assisting customers in stores and the disabled in their homes. I am a navigator, mapping our world 1 millimeter at a time, and making even the largest self-driving vehicles safer for the long haul. I am a creator, learning to paint from the masters and applying their styles to create original works of art. I am a teacher, analyzing 500,000 player moves every game to identify strengths and weaknesses. And a learner, discovering new strategies through complex games. I am even the composer of the music you're hearing. I am AI, brought to life by NVIDIA, deep learning, brilliant minds everywhere.
So So since 2012, we've moved from a position where neural networks were perceived as a failed experiment of machine learning to a position where they are defeating world champions in very complex games, such as Dota, where they can interpret a wide range of image, audio, text data, and do it in many cases much better than humans. That is why we're seeing headlines like that. So China investing literally tens of hundreds of billions of US dollars in AI research, UAE appointing a minister in artificial intelligence, Microsoft making AI one of the top priorities in terms of technology development. And Andrew Ng saying things like that. Andrew Ng is one of the most established machine learning researchers in the field. And so a lot of you would have used his latent Dirichlet allocation on a day-to-day basis. Just as electricity transforming almost everything 100 years ago, today actually I have a hard time thinking of an industry that I don't think AI will transform in the next several years. And we're seeing that. So as you saw there, we had examples of literally every possible application area. And after I show you the heuristics for choosing the feasible AI projects, you'll understand why. So in the last 15 minutes, and then I'll leave a couple minutes for questions, I'll give you a couple heuristics that you can use to assess what is possible today and what might not be necessarily the best idea or what might be more difficult to do today. So what makes AI projects successful? So at this point of time, so today, majority of application areas where we see success, neural networks are used as supervised learning algorithm. So that means that you need to, if you have a problem, you need to have both the data set and the labels. And that can be, that limits you to some extent, but if you look how loosely defined those can be, then you'll see that a lot of problems can be very easily defined like that. So in case of image labeling, you need images as your data and names of objects in those images as labels. A neural network is learning the function from the image to the label. If you want to do speech recognition, you give the neural network the raw audio form, and you give the text transcription of what was said in that text as a label. If you have a mortgage application, then you can give it a mortgage risk then as a label. In translation cases, you can give it a sentence in English as data and sentence in French as a label. So a lot of problems can be formulated like that, and at this point of time, those algorithms that can be formulated like that are much more successful than unsupervised learning problems. So unsupervised learning problems are still an active area of research. Neural networks thrive where you have problems with little amount of noise, where you have extremely complex data structures, like images, where you have layers and layers of representation, but limited amount of noise. So if I show you a picture of a cat, you as a human being, you know that that's a cat. There is very little amount of noise around whether it's a cat or it's not a cat, unless it's an exotic species, but that's more due to your knowledge of cats than your ability to distinguish a cat. That is changing slowly, so self-normalizing neural networks allow us to tackle problems that are much more noisy than the ones that we used to, and also non-stationary problems. But in principle, currently they thrive for problems where there is little inherent noise in them. That's a very good heuristic that Google product development team was using, and I found it very useful. So at this moment of time, if a typical person can carry out an activity with less than a second of thought, that's usually a very good candidate. A lot of problems have this property. So for example, driving a car. We sit in front of a steering wheel and we just drive. When I show a doctor an X-ray of a chest cavity, he'll know how to interpret it instantaneously. The doctor doesn't have to elaborate on that problem. If the problem that you have at hand is not like that, then they are usually quite complex. So if you can tick a box against this heuristic, you're in a very good position. And in fact, this constitutes more than 80% of our day-to-day problems. You need to have a lot of data. And this is very important. Without a large data set, you're very unlikely to succeed. And that's important because in a lot of problems, obtaining that data can be costly. So if you think about labeling 10 million pictures of cats, you can, I guess, pay a bunch of students to do it in a couple of months. If you want to annotate 1 billion of CT scans, pixel by pixel, paying 1,000 doctors to do that might be expensive. It's not impossible, yet it might be expensive, so bearing that in mind as you choose problems is important. So if the dataset requires skilled label to produce labels, this limits your scale and affects your cost significantly. And how much data you need? That's a quote from a very good book that I would recommend called Deep Learning, written by Ian Goodfellow and Joshua Bengio and a couple other authors. As of 2016, so that book was published in December, you will need at least 5,000 labeled examples per category. And to achieve human-level performance, at least 10 million labeled examples. It's a heuristic, so it will not always work, and you can cheat sometimes by transfer learning from other problems, so using a different data set to pre-train your neural network and then just fine-tune it to your problem. But that's a good thing to bear in mind, because that gives you an idea of a scale. And working with smaller data sets than that is an important research area. So expect complexity. This is what I was trying to say. You need to ask yourself very honestly, what level of accuracy do you need? And how do you define accuracy? And you need to do it on day one. Because as I've mentioned earlier, there is this very expensive log linear relationship between the amount of data that you'll need and accuracy. So if your accuracy is extremely high, like for example in automotive context, that might be an expensive problem to solve. So if you look at, let's say, public announcements from BMW, they are reporting data sets of hundreds of petabytes, yes? Because the need to have the performance of those systems at that high level. So if you can handle the lower accuracy, and a lot of problems can. So for example, translation problem, you don't need like 99.999999999% accuracy, then you can usually trade it off with data and cost. And always you should ask yourself a question, can something simpler work? So there are a lot of good classical machine learning algorithms, and you should always use them as a benchmark. So choose a tool that you know how to use really, really well. Try to solve the problem with that tool, and only when you don't achieve what you want, or you believe that you can achieve much more with neural networks, try to use them, always having this as your benchmark in the back of your head. So those are the heuristic. Very simple, but will allow you to very quickly take an idea and decide very quickly, does it seem like a good candidate for this technology or not? Or is there an inherent complexity? So call to action, talk to us about your use case. We don't sell professional services, we don't sell any products. Dell, HP, and others will sell our products. Microsoft will sell our products, or Google, through their cloud. We want you to succeed so that you will eventually, at some point of time, buy those products from those guys. So come to us. We have a partner booth at the back. I'm happy to answer any questions you have. Ask about potential proof of concepts. We have a rich partner network that can help you with everything from infrastructure to professional services. We have a massive training program called Deep Learning Institute as well, which I'll show you in a second. Actually, with more than, I think, 80 specialized deep learning courses, everything from fundamentals to medical imaging to AI in financial markets. Just take advantage of it. They are very affordable. A single course will be like $5 to $10 just to compensate the infrastructure cost that is used. We're available literally everywhere. So yeah, 10 minutes left. And I have 2 slides, and then we have questions. We're in every data center, so whether your organization is buying hardware from Hewlett-Packard, Dell, whether you want to deploy to Microsoft or Azure, it doesn't matter. We're present literally in every data center and in every cloud. We have a bunch of hardware products that you can use that were designed exclusively for deep learning. Take advantage of Deep Learning Institute. Use our containers. So for those of you who know what deep learning frameworks are, so those are just software packages that you can use to train those neural networks. on a monthly basis, we support all of them. So TensorFlow, Caffe, Caffe2, Torch, PyTorch, Tiano, Paddle, Chainer, whatever you're using, it's there and it's for you to use. Just register, no strings attached. Every month, correctly built and highly optimized deep learning framework for you to use for free. And talk to us. Talk to us today. Follow up with us and come to our conferences. Unfortunately, or maybe fortunately, we just had our conference in Europe, in Munich, a couple weeks ago. Next one is in Japan, and we especially invite you to our biggest event in the United States. That event will be predominantly focused on artificial intelligence. There will be part about computer graphics and high-performance computing, but a massive part of it will be about artificial intelligence. So come, have a look what's happening, talk to us, and questions, I guess. Do we have questions? Do we have the microphone? I think we do have a microphone. Now, do we have questions? If we don't have questions, come to our booth. We're here to help. Thank you kindly.